we've got this range of views. We can see different wavelengths, going from radio waves through infrared, through visible, and then X rays and gammas. Um, and we can see the different formations of gas and dust and the different steps in the recycling process. And so we're going to look and compare the visible light, where what we can see is there's lots of stuff scattering and absorbing light. There's lots of dust and gas, and you can see the clouds in that view. We're going to compare it to all these others. And so in radio waves, what we're seeing is the atomic hydrogen that's cooling down, it's settling into a disk, and we can see where that shows up. And of course, it's more dense towards the center, and but that's showing you where these clouds are at. Then, looking for carbon monoxide tells you where the molecular clouds are, and you can kind of see that again all along the disk, more towards the center. But yeah, in infrared, now we're seeing where the stars are heating the dust and gas. And we're seeing that dust and gas glow, and so you can see, effectively what you're seeing is where the dust and gas is here. And so, going higher frequency, shorter wavelength infrared, now you can see lots of the background stars that have formed. Where in the visible light you can't see them because they're behind a cloud. But you can see them here, and so you can see where all the stars are. So on X-ray, you can see that there's this thin, dark band that goes across, and you can see the bright areas. And the bright areas are where the hot gas is forming above and below the disk. What we're seeing, the dark areas, the disk, and the light areas are where we're seeing the glowing gas. And then in gamma rays, we're seeing when the star dies, when supernovas occur, we're seeing the gamma rays are formed when rays from the supernova are colliding with stuff in the gas clouds. So that's the disk, right? The disk has a lot of star formation, and we'd like to know where they form in the galaxy. We talked a little bit about the structures, the molecular clouds, the types of and now we'll talk about some types of nebula. Ionization nebula is where the gas gets ionized by the newly forming stars. In particular, the high mass stars are very energetic, and the gas glows because it's absorbing and re-emitting energy. Reflection nebula are just scattering light from stars, and when it scatters light, the blue light's the easiest to scatter. The red light passes through, and so most of the light we see is going to be scattered towards us, and so the nebulas are going to look blue. And so here is, you've seen this before. This is the Horsehead Nebula, and below here, this blue patch is a reflection nebula, and in the Horsehead, at the very top, and you can kind of see the mane going down there, and the underside of the nose and mouth. Those are your ionization nebulas. That's where the gas and dust is glowing because stuff behind it is heating it up. So, if we look at the sky in total, look at the entire galaxy, what we see is most of the ionization nebulas, most of the high mass stars causing the gas and dust to glow, is occurring in the disk. And there's lots and lots. So, to be clear, you see lots of blue stars here. You need to be careful. Note there's lots of foreground stars. Is we want to look at the stuff in the back. But in general, what we see in this sort of layout is blue stars are going to form in the disk, and there's not going to be blue stars in the halo. Right? The halo is kind of harder to see here. It's not a great image for that, but that's okay. When we look at other galaxies, all right, remember we're looking at our galaxy face on. When we look at galaxies, sorry, we're looking at our galaxy edge on because we're in it. When we look at face on galaxies, it makes more sense what's going on. Is these spirals, and this is the whirlpool galaxy, and it looks like a whirlpool. It looks like everything's spiraling inwards. I realize I'm using my hands trying to demonstrate stuff, so yeah. As this stuff spirals in, you notice that there's bands in the spirals of blue stars. Blue stars occur in the disk, and there's a pattern to it. There's ionization nebula on the very edge of each of each spiral, and then you see the blue stars form, and then the blue stars are going to blow up. They're going to supernova, and you're going to have gas clouds hanging out on the trailing edge of the spiral. Now, note if you look at the bulge and you look at the spaces between spirals, there's not as much. There's not as much uh, blue stars. Is that this is more reddish. Spiral arms are going to represent waves of star formation. They're going to rotate around as the galaxy rotates. And what happens is the leading edge of the wave is going to compress the gas clouds. It's going to form the ionization nebula. And then the blue stars are going to trail out of those spirals. And eventually you're going to have new cloud formations as these stars die off. So when we look at the galaxy, that this is all giving us clues to how we think the galaxy formed. When we look in the disk, we see lots of heavy elements, and when we look in the halo, there's 10 or 100 times less heavy elements. We're talking oxygen and iron, the stuff that forms in supernovas, stuff that forms in very massive stars. So the halo's population is very low in heavy elements because it's all old stars. It's all very small red stars. In the disk, we have lots of heavy elements because we have lots of star formation. We have essentially 10 to 100 times the we have multiple cycles of star formation where in Halo it's formed once and that's it. And that's our interpretation of this is as the galaxy formed, the Halo stars formed first. And they were the only cycle of star formation in the Halo. The remaining stuff ended up in the disk and formed several cycles of star formation. So that kind of gives us an idea that there was some sort of collapse. And this is going into, the same sort of things how stars form, how our solar system formed, is lots of collapse into a small flat disk. All right. Our galaxy was a massive intergalactic cloud of gas. And you can think this is like a molecular cloud. Something's going to initiate a collapse. And as it collapses, there's variations in density. Some of these areas are going to be dense enough to form stars pretty quickly. And so you get halo stars forming. And they're spherical. Spherical because they're basically random as the cloud collapses. So at the very start of the collapse, you get halo stars forming. But the material's still going to collapse towards the center. And so all the gas and dust around these stars are going to fall inwards. And a collapsing cloud that's rotating is going to conserve that angular momentum and it's going to average out the random motions and just keep angular velocity. And so you're going to end up with a small flat disk. This is a massive flat disk, but smaller than the original cloud. And so this is going to be very dense in gas and dust in the disk. And so you're going to have ongoing star formation. You're going to have stars form, and then when they die, it's going to reseed the material out into the clouds, and then there's going to form new stars from that. And so you end up with this spinning disk around the middle. And so that explains, that is a model that explains why we see um, star formation in a disk in these spirals, but not in the halo stars. This is a super oversimplified model. When we get to the next chapter, we're going to talk about how there are other types of galaxies. And they don't necessarily look the way this does. And some of it's because they're older galaxies, some of it's because they're collisions between galaxies, some of it is we don't know. But this model kind of does well to explain, it's built for our galaxy. Um, and if you model a bit closer, you do computer modeling of the formation, you end up with an understanding that the cloud is clumpy and halo stars form in clumps, and then the clumps kind of form this ball uh, around the galaxy. So in the center of our galaxy, we didn't talk about the bulge very much. There are many, 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 many stars there. We're going to address this picture here in a bit. But there's lots and lots of stars in the bulge. There's lots of older stars in the bulge. And there's lots of stars orbiting some central object. So this is a look at the stars and radio waves. In particular, the thing we care about is the central yellow bright spark, what's labeled here SGRA. That's Sagittarius A. This is all in the constellation Sagittarius, because that's the direction of the center of the galaxy. And there's a lot of stuff that we don't know what this is. We have a reasonable idea what this thing is at the center. Here's the same view. This central point correlates with the one we're talking about here. This central point is the center of the galaxy. But this is all in a small area around the center. And there's lots of X-ray sources, lots of white dwarfs, lots of neutron stars, lots of stellar black holes, and lots of clouds of gas and stuff around. And so if we zoom in on that, all right, this is in X-rays. This is in radio waves, and we see a radio source. Lots of hot ionized gas. Something is putting out a lot of energy and ionizing gas and causing it to radiate in radio waves. And this is the same spot we're talking about. This is the center of the galaxy. So we zoom in on that, right? All these images are the same spot. And we're going to zoom in on it. Right. We look at infrared and we look at radio waves. I do recommend looking at these videos as we go on. And then from radio waves to looking at the emissions from the swirling gas. And we're zooming in further. Eventually, we get down to where we can see individual stars orbiting something. This is the space of a light year. We're going to zoom further in. So this space here is 1600 astronomical units. So some of these are on the order of 5,000 AU, some like half a light year. And so these stars are orbiting some central spot. Now, 1600 AU is on the order of long period comets, and those things take thousands of years to orbit. Well, like when we measure their orbits, their periods are going to be tens of thousands of years. For now, and that's because it has a single star, a single solar mass uh, that's attracting, gravitationally holding on to them in orbit. But whatever this object here is significantly more massive because we're making these measurements significant fractions of the orbit are occurring over the space of like 15 years. This is from 95 to 2010. And so these orbits can't be very long. They're on the order of 50 or 60 years, not tens of thousands of years. And when we go back and do the calculations for what's going on here, we end up with the object here at the center is about 4 million solar masses. And we can't see it. There's no light coming from it. Something that big and that non radiating is probably a black hole. And so, we can look, this is another image. This is over 20 years of data, and it fills out more. And these measures are, this is a tenth of an arc second. This is 2/10 of an arc second. So this is down at 800 AU at the same scale. These are very tight, very fast orbits around a point that's not glowing. This has to be some sort of massive object. It's not glowing. That's a black hole. And we can see X-ray sources coming from that. Essentially, as stuff falls in, it's basically ripped off of other objects, and we see flares of X-rays coming from it. So I do recommend you watch these videos that are linked. They're, as I remember, they're fairly good. They're showing, at least one of them is showing the actual orbit over time. There's a image of it, and there's some more explanations of this. I believe this concludes. Yep, it concludes chapter 19. We'll come back. We'll talk about different types of galaxies and how we know where they are.